to the CH1601 video series. In this video, we will continue to focus on carbonyl nucleophilic addition reactions. Firstly, we will look at the formation of hemiacetals formed by reaction between an alcohol and a carbonyl compound. This follows a similar mechanistic pathway as the hydration reaction covered in video 15. The electron-rich oxygen atom of the alcohol adds to the electrophilic carbon atom of the carbonyl group. A tetrahedral intermediate is formed, followed by a proton transfer, as demonstrated here, to yield our hemiacetal product. Similar to the hydration reaction, the synthesis of hemiacetals can be sped up using an acid or a base catalyst. The acid-catalyzed mechanistic pathway is drawn here, where the proton from the acid reacts with a lone pair from the oxygen of the carbonyl group. Remember, this makes the electrophilic carbonyl species more reactive because of the resonance form observed. Following addition of the alcohol, a proton is lost to regenerate the acid catalyst, and the hemiacetal product is formed. All steps in this reaction are reversible. Meanwhile, in the presence of a base catalyst, we have a more reactive nucleophilic species by producing an electron-rich ion with a formal negative charge. Addition of the nucleophile to the carbonyl occurs, and the negatively charged oxygen in the tetrahedral intermediate species picks up a proton from a protonated base, yielding the hemiacetal product and regenerating the base catalyst. Once again, all steps in this reaction are reversible. In certain conditions, specifically when there is excess alcohol and an acid catalyst, a hemiacetal can be converted into an acetal product. Take care when drawing hemiacetals and acetals, because although they might look quite similar, they contain different functional groups. The mechanism for the synthesis of an acetal is quite interesting, one which we will talk through step by step. We start with the reaction pathway for the synthesis of a hemiacetal. Remember, this can occur with either an acid or base catalyst. For the synthesis of an acetal from a hemiacetal, only an acid catalyst can be used. This is because we cannot simply kick off this group as a hydroxide ion, since it is a poor leaving group. Therefore, it is necessary to protonate the OH group first with the acid catalyst to produce a suitable leaving group. An adjacent lone pair from the other oxygen pushes in and forces the loss of the H2O leaving group. This produces a positively charged intermediate species known as an oxonium ion, which, of course, has a resonance form which makes the electrophilic carbon very reactive. It is really crucial that you include this oxonium ion as part of your mechanism in any given acetal formation reaction. A second alcohol molecule attacks the electrophilic carbon center, forming a tetrahedral intermediate species. In the final step of this reversible reaction, a proton is lost to regenerate the acid catalyst and yield the acetal product. This unique mechanistic pathway makes for some quite interesting reactions. For example, the synthesis of cyclic acetals. Cyclic acetals are produced using diols, which are compounds with two OH groups. In this type of reaction, we start with a carbonyl compound and produce a hemiacetal intermediate. Then, going via the oxonium ion once again, the cyclic acetal product is formed by addition of the second OH group and subsequent loss of a proton. It would be worth pointing out here that the intramolecular SN2 reaction does not occur. This is quite a common mistake, so please don't fall into the trap. Remember that we must always proceed via the oxonium ion instead. We've spent some time looking at reactions between carbonyl compounds and alcohols. Now we're going to look at the reaction between a carbonyl compound and a primary amine. This type of reaction results in the formation of an imine. Let's take a look at the mechanism. Amines are generally more nucleophilic than alcohols, since nitrogen is less electronegative than oxygen, and therefore holds its lone pair of electrons less tightly. This means that an acid catalyst is not required in the first step of the reaction. The primary amine directly adds to the electrophilic carbon atom of the carbonyl group, forming a tetrahedral species. Following a proton transfer, a hemiaminyl intermediate is formed. Now we want to lose this OH group, but in order to make a good leaving group, we must protonate it using an acid catalyst. The adjacent lone pair in the nitrogen pushes in and forces the loss of the H2O leaving group. This forms a positively charged intermediate species known as an iminium ion. It is really crucial that you include this iminium ion as part of your mechanism in any given imine formation reaction. In the final step of this reversible reaction, the loss of a proton regenerates the acid catalyst and yields the imine product. Hopefully you can recognize that this mechanism follows a largely similar pathway to that of an acetal. The only difference is we only add one equivalent of a primary amine rather than two equivalents of an alcohol. This is because the iminium ion contains an extra proton, whereas the oxonium ion does not, making the electrophilic carbon center more reactive. In the synthesis of an imine, we observe an optimal pH of around 5 or 6. At low pH, i.e. very acidic conditions, the primary amine will be protonated and therefore cannot act as an effective nucleophile. The nitrogen atom donates its lone pair of electrons to a hydrogen ion. The rate-determining step here is the initial nucleophilic addition. At high pH, i.e. less acidic conditions, there are not enough acidic protons to turn the OH group into a good leaving group. The rate-determining step in this instance is the loss of the H2O leaving group. At pH 5 or 6, there is a Goldilocks situation. We have enough acidic protons present, but not too many. The last reaction we will look at in this video is the reaction between a secondary amine and a carbonyl compound. While a primary amine forms an imine product, a secondary amine forms an enamine product. The mechanistic pathway for an enamine formation is the same as imine formation up to a point. We once again directly add the nucleophilic species to the carbon atom of the carbonyl group and transfer a proton. An acid catalyst protonates the OH group and we form an iminium ion. The final step of this reversible reaction involves the loss of an adjacent proton, which quenches the positive charge on the nitrogen, regenerating the acid catalyst and forming the enamine product. It is this step which is unique to enamine formation, so ensure you pay particular attention here. Try the quiz to test your knowledge on the reactions discussed in this video.